but why don't we get started in the meantime? So Leo will tell us about the philology.
Okay, so thanks so much. So this talk, or at least the program that I want to, of which I would discuss some aspects, is very similar to the talk I gave in Purdue in the spring. So again, the overarching thing is the same, but the technical details are quite different. So I'm going to report basically on two papers that appear in September with my grad student, Vimal Ratti, and then all the collaborators and Jim Liu, and he's actually an undergraduate student who went to Michigan for some. So what I want to discuss is how basically topics, some different aspects of holography once you go beyond the leading term. Because of course the talk is fairly technical, I want to first again clarify what is it that I'm trying to do, and this is this slide, which is the motivation. So right now we have seen a lot of applications of localization in supersymmetric field theories, and usually they give you an exact result in a supersymmetric field theory. So you get something that is some expectation value that is good for any coupling and for a large range of parameters. And my motivation is, okay, now that I have all this data, can I use it to understand a little better the ADS-CFT correspondence? Because some of the field theories that for which localization applies do have a gravity dual, okay? And in particular, so this is sort of like the main equation of ADS-CFT. We say that the partition function on the field theory is given by the partition function of a string with some boundary conditions. Okay, and most of the calculations that have been done in ADS-CFT sort of stop here. But what I would like to do is to, well, in fact, we do more, right? So because we cannot compute in a string theory, we compute in a supergravity sort of regime. And that's a very classical limit. But if I'm interested in, because I have an exact expression here, I can extrapolate it to the regime where gravity should be valid. So I should be able to recover the field theory answer using perhaps semi-classical quantization on the gravity side. And there you will see that there are many questions that appear, and not everything is not all is well in this part of ADS-CFT. So that's where I want to spend more time. Okay. So and again, my goal is not to find some counterexample in ADS-CFT. My goal is to take this as the experimental value, and then try to explore what are the ingredients in my theory that are not yet working, that I don't yet fully understand, and use field theory results as a guidance for what I need to incorporate when I do semi-classical quantization. Okay, so that's my goal. And again, what I talked about in Purdue in April, there's some. It's not just a masochistic technical exercise that one does on this part. In fact, you start seeing some new structures of a string perturbation theory and in the bulk. And one that is particularly interesting there, I see some hints, and I will go on this, that there is also something along the lines of bulk localization. Okay, so that's, again, this is sort of like the big picture, and then I'm going to proceed with some concrete examples of these calculations. Okay. But I want this motivation to be very clear. Okay, so this is my outline. I will start by reminding you of a very old puzzle in ADS-CFT, which has to do with the Wilson loop in the fundamental representation for n equal 4. And then the new results that I want to report today are essentially about higher rank Wilson loops in ABJN theory. So I will show you the field theory calculation. That was the paper with Jim and Johnny Kottmeyer. And then I will show you some progress in the holographic computation. But again, because this is sort of a program that I'm very invested in, I will show you some other questions in this area. And if I have time, and I hope I do, I will tell you how this kind of calculation start teaching us that there's some things we have not done properly in ADS-CFT, like for example, holographic renormalization. Okay. So that's my plan. So here's the introduction of sort of the operator that I'm going to focus on. So it's the Wilson loop. It's a very important operator in any gauge theory. It's a non-local operator, so it depends on some contour, and I can write it in some representation. It's very concrete in the sense that it is a good order parameter for confinement. And what I want to do, as I said in my motivational slide, I want to compute not just the leading term, I want to compute sub-leading corrections. So this was done in QCD, and those in that context go as Lusher terms. So you have the confining potential is proportional to the distance between two quarks, and then the quantum correction is inversely proportional to that distance. So these are the kind of things that we want to do in this context of ADS-CFT. So we already know, or at least understand, the leading piece, and I want to move into the sub-leading piece. Okay, so let me remind you, this is the puzzle that I think everybody should know. So I incorporated at the beginning of most of my talks. So they have BPS Wilson loop in n equal 4. So it's a very, so the simplest Wilson loop that you can think of in the context of ADS-CFT. So n equal 4 is, of course, I expect well known. It's a vector theory with chiral multiplets. So the data that I need to define this Wilson loop is a curve C in and a representation, as I said before. Because I'm in n equal 4, it's a supersymmetric theory. If I want my Wilson loop to be supersymmetric, then I need to add this coupling here. Then this is adjoint, so everything works very nicely. Now, if you ask when is this operator supersymmetric, you get that C has to be a straight line or a circle, and this operator was one of the first discussed around 2000 by Drucker and Gross and Erickson, Seminoff, and Zarembo. So they're already using basically Feynman diagram techniques. They already understood that there's a very simplified structure when you compute the expectation value of this operator.
That straight line or circle means as a curve in the 10-dimensional space of the
No,
x's and y's?
No. This is a statement about n equal 4. So I'm just talking. So here are the couplings. So I can. So this is my curve live in. Okay, so you mean 10-dimensional in this sense?
In that sense.
Yes, it is 10-dimensional in that sense.
But it's a straight.
But in fact, it's a point in the 6-dimensional part.
Oh, so does it have to be supersymmetric? It has to be at a point?
Yes.
Yeah, I think that their original loop is set at constant y, right?
Yes.
Yeah.
So in fact, the reason why this guy, since this is, I would not take my an hour and a half, but I do want to answer some detail. So the reason why these guys realized that something interesting was happening is because they computed the effective propagator, and there's a cancellation between the gauge field and the scalar. So the scalar is crucial to have it in a particular gauge. So it's a way to see.
So to have a phi 1 in that second expression, doesn't that mean that you're not at a point in the y in the y directions? Because so that yi dot is a constant, y1 dot. I'm just it's a very naive question. I'm just trying to figure out what curve in space-time and the internal y space.
So I'm taking. You're saying it's a.
So it's not at a point then in the internal space. It's actually.
No, it is a point. So this dot doesn't go here. So here I need a dot because this is coupling to a vector, like velocity if you wish. So this is ds. So it's not a dot. It's just y. Sorry.
Oh, okay.
Okay, I think there is modulus of x dot instead of it's y and then modulus of x dot.
Yeah.
Oh, okay.
Oh, so it's y.
Y I
dx.
dx. Okay, got it.
Okay. So Of course, so this was a conjecture, but then later on it was proven using, as I said at the beginning, supersymmetric localization by Peston, that the expectation value of a circular Wilson loop in the fundamental representation can be computed exactly in terms of Laguerre polynomials, okay, for any lambda and any n. And then with my agenda to compare with ADS-CFT, I want to expand large n and then even large lambda. Okay, and what I see, this is what I would call the classical piece. If you're thinking again about QCD, this would be the linear in the quartz separation part, and then these are the parts that I want to call a Lusher term for n over 4, more or less. Okay, so that's those I want to. Those are correction in the large lambda limit, and those I want to retrieve using ADS-CFT. Okay. So as I said, this is an old puzzle. This is not something I did. This is something that people like Drucker, Gross, and Salin tried.
There's the order in which you take the large n limit. So you take large n, so g goes small, and then you take large lambda.
Yes.
So you can't do large lambda and large n. Like.
So in the field theory, I have exact expression, so that's the good thing. So I expand in this order because I want to connect with gravity, and I think that's what's going on in gravity. But that's an advantage of really, this is a new thing. So people can, one question is, why are you interested in this now? Because now we have data from localization. Otherwise, string theory gives you might do a computation, but there's nothing really to compare. No, field theory is much more, as I said, it's like the experiment. So it gives you the answer in a big range of parameters.
But, could you show again the previous slide?
Yes.
Yeah, I thought, so you're saying that the 3/4 log lambda was never reproduced?
The 3/4 Los lambda has never been reproduced.
I thought it comes from some sort of zero mode.
Yes, so there's an argument that it comes from Gauss zero modes in the wool sheet. That is true. That could be true, but I will give you.
I recall some Saitlin paper where.
Yes, it's this paper. Drucker, Salin, Gross, Salin, where they claim that this 3/4 comes from Gauss zero modes in the string wool sheet.
Using this.
But even so, if you so I have more to say about that because I can do the same computation in ABJM, and I can see that it's not really 3/4. So there must be something. But I can.
Yeah, usually such prefactors come from counting some zero modes.
Yes. Okay. So if I want to look at the holographic computation, again, this was done already more than a decade ago, and continues to be done. So this is Martin also looked at this problem, and Salin more recently. So essentially, you want to look at the fluctuations of the string. Your string. I will show you more examples, more concrete example as the talk goes on. But roughly, you want to compute the one loop effective function of the quadratic fluctuations of the string around its classical solution. And essentially, here are the determinants. I'm very intuitive, right? So I have 5 massless modes because I have a point on S5. And then I have 3 massive modes that essentially describe embedding ADS2 inside ADS5. ADS2 is the work volume of this supersymmetric worksheet. This computation, the answer to the one loop computation essentially gives you this minus half log of 2 pi. So let me put the two things together. So they don't agree. Again, the missing log of lambda term has been discussed extensively as attributed to zero modes in string perturbation theory. So as you see, at least it's certainly not something that you can see clearly from supergravity. So that tells you that when you want to do this semi-classical computation, you have to be aware of something extra, perhaps this topological structure of the wall sheet. But even the finite piece doesn't match. Of course, you can argue, right? You can argue that there might be some scheme. I will address that at the end of the talk if I have time. But essentially, this is how this is the status of this problem as of today. And again, I don't think that there's been mistake. Different people have tackled this problem with different techniques. As I said, these guys use heat kernel technique. Martin used something called Gelfand-Jaglom to compute it. Peter Selling used also some sort of heat kernel techniques, and everybody gets the same answer, but the answer does not match the field theory. Okay, so one possibility, as I said, if I have time at the end, I will talk about, is that perhaps the way that we are regulating divergences in the worldsheet is not completely correct, and we need to go back and revisit that, because that's the source. And if I have time, I will discuss that. It's quite interesting, actually. Okay, so this is the situation. This is my main motivation, what I'm interested in this class of problems. So the simplest thing is not giving you a clean on-the-nose agreement. So there are subtleties. Some of them we attribute to part of a string perturbation theory that we don't know in curved space. But in the meantime, I think that one important approach is to try to study similar problems in perhaps a slightly different context. And that's, so again, in April, I gave you a talk about different projects that I have carried in the context of N=4, but today I'll talk about ABGM. Okay, so why, if N=4, which is supposedly simpler, is not working, why consider this? Well, as I said, I'm looking for more experimental data. I want to understand perhaps a different situation. I can get rid of some of the subtlety. More interestingly for me is that ABGM, as I will show you in a second, has more parameters. So you can try to compute in different regimes and understand what is different in the different regimes. There's also, because the theory contains Chern-Simons, you will see that it inherits some sort of topological intricacies that are typical of Chern-Simons. And in general, even though it seems to be simpler, there are many interesting questions that have not been answered. Question at the level of the classical solution, not just quantum correction, that I think are worth clarifying. Okay, so here's my one slide about ABGM. So ABGM is a three-dimensional theory of Chern-Simons matter with this gauge group, UN cross UN. And the Chern-Simons levels are k and minus k. And then I also have 4 complex scalar, Ci, and they transform in the bifundamental of this gauge group, UN cross UN, in n bar, and of course, the complex conjugate n bar n. Now, very quickly, I want to construct, so I guess then now I did it better, the Wilson loop. So I want to construct the supersymmetric Wilson loop in this theory. And again, this part is obvious. What might not be completely obvious is this part. But here you get sort of inspiration for the N=4. So you want to use the bifundamental to construct something that kind of looks like an adjoint. And then it was already in 2008 checked by 3 different groups that this Wilson loop is supersymmetric. It preserves 1/6 of the supersymmetry. So N=4. So Chern-Simons is N=6. This ABGM is N=6. 24 supercharges. Let's keep that counting. But it preserves 1/6 of the supersymmetry if Mij, this matrix here, take this form, and then the contour is a straight line or a circle. So this is the object that I want to discuss. But okay. So one important result, which is similar to the situation in N=4, is that the vacuum expectation value of supersymmetric operators can be computed via localization, and it reduces to a matrix model like this. Okay, so what you see here is roughly this comes from the Chern-Simons level. So these are I have 2 gauge groups, so I can think now of the eigenvalues of the matrix corresponding to the 2 UN. Okay, and then I have a kind of a van der Monde determinant, which is this part here. So this is the matrix model. In N=4, life was simpler because it was just a Gaussian matrix model. So this matrix model is different, but nevertheless, it's well understood. And again, it's since 2009 has been written and explored carefully. Okay, so the objects that I want to compute using the matrix model are these 2 kinds of Wilson loops. A Wilson loop in the symmetric representation, SM, and in the antisymmetric representation. And essentially, once I have written my operators in the eigenvalue basis, they are essentially given by this expression. The main difference is ordering of the eigenvalues. So, but of course, instead of doing this computation, which is a little more complicated, what the standard approach is to define some generating functions for these Wilson loops. These are the generating functions. As you can see, essentially, this is like Fermi-Dirac distribution and Bose-Einstein distribution. They give you the symmetric, the k-symmetric and k-antisymmetric representation. And then these are the generating functions. So what I really need to extract is the coefficient of t to the k in this expansion, and that I do using some contour integral. Okay, that's what I need to do to compute the expectation values of Wilson loop in the symmetric and antisymmetric representation of ABJ. Okay, any question?
Maybe what are the new ones?
So I have two gauge groups, and I'm calling the eigenvalues of one mu and the eigenvalue of the other nu.
Of the UN matrix.
Of the UN cross UN matrix. So I have two gauge groups. So because I want to use large n, what I need to do, of course, I wrote it in terms of eigenvalues, but that are discrete, of course, but I'm going to take n large in a way that I can approximate, I can describe the eigenvalues by an eigenvalue distribution. Again, this is very standard for the Gaussian matrix model. There you might remember that your eigenvalue density is the Wigner semicircle distribution. So this distribution is a lot more complicated. It's arctange with this square root, but this was discussed by Marinho and Putrov already again in 2009. Again, this is a kind of convoluted but not complicated. Okay, so you have the function, and then these parameters are related to lambda, and lambda is related to kappa in the way that I have written here. It's not very complicated. It's just that it's messy. But it's known, okay? The function is known. Now, working with this function, this is valid for all values of lambda, but it's hard. So what I'm going to do, I'm going to take a limit in which I take lambda to be large. Then this equation that I have before with the hypergeometric function becomes, simplifies a lot, and I get a relationship like this here. And then this is now the eigenvalue distribution, which is a continuous variable, and it goes between minus mu star and mu star. Mu star is computed in this way. So essentially, in this large lambda limit, this is my expression for the eigenvalue distribution, which essentially becomes some constant. If I assume now I'm making a small assumption that some of the distribution doesn't go to the edges where the cuts are, but it's smart. Now the interesting thing, or one thing to notice, is that now basically my eigenvalue distribution is a constant, so it's a constant distribution and then goes to 0 at the end of the cut. But this is precisely what Igor and Chris Herzog found when they studied also the ABGN in the M-theory limit. It's a completely different limit, but yet the distribution also goes to a constant. So the calculations that I do will also be valid in the M-theory limit. So that's one added thing that I advertise about ABGM, that it allows you to consider various limits. Okay, so now, again, this is the expression that I explained before. So I have the Fermi-Dirac and Bose-Einstein distribution for the antisymmetric and symmetric. I need to compute the M. Now M is the number of boxes in the Young diagram, if you wish, for the symmetric and antisymmetric. This integral, when rho mu is a constant, give me some dilog. And essentially now what I need to do is to evaluate this integral. Okay? This is a calculus exercise. The simplest way to do is to use a steepest descent kind of method. And again, if you do it for the antisymmetric representation, this is the equation that you get. You can try to expand for large lambda, because that's precise. I already assumed that rho being a constant was already large lambda, so I want to be consistent, go to large lambda. This is my expression. and I can compute, and okay, so there's, the dialog has some cuts, so I have to be careful, but for the antisymmetric case, it's very simple. Here's the answer, okay, that I evaluate at saddle point. So here's the leading piece, okay. And I can, of course, this is saddle point, so I take second derivative, and I can evaluate also the 1/n correction. So with these techniques, I have, for the antisymmetric representation, the leading piece and the correction. Okay. So that's so this result was not known. This is new, and so what I'm going to do now is I'm going to show you with less steps the same computation for the symmetric, and this is sort of like this is part of the paper that I wrote with Jim. So it's a computation using the ABJ matrix model of the expectation value of these Wilson loops in the antisymmetric and symmetric representation. So again, for the antisymmetric, I can go, it's as I said, so the steepest descent doesn't quite work. You have to deform the contour, but again, this is not much more than a little bit of calculus. Here, the value comes from the jump across the cut, and here it is. So this is the leading piece, and here we have an expression for the sun-leading piece. And again, all this is obtained in the large lambda limit. So these are new results. Of course, what I want to do in the field theory side, it was fairly easy. So I have some matrix model. I know how to do this computation. All that is really required is that I go to, it simplifies if I go to the large lambda. And there I have computed this quantity. So now I want to go to the holographic side and see how far I can get. Yes?
So in the previous slide, you have log lambda times a bunch of stuff.
Yes.
So why do we trust all those other things inside the log? Or just the fact that it's 1/2 log lambda?
Good. So I'm trying. That's good. So essentially, maybe. Okay. So I don't. Yeah. So this is what I'm trying to evaluate, and I have written this because I want to use a steepest descent. So I want to use large n, and here f was essentially m, the number of boxes in the representation divided by n. So I explicitly working in a limit where this is a fixed constant. So n is large, and m, this number of the representation divided by n, is a fixed number. So because this is the limit in which I'm working, I keep everything that contains these parameters. And lambda is a slightly different limit. That has to do with the fact that I'm working in type 2a. So in that limit, then lambda is k/n, and that is also fixed. So I keep things that I had decided that they're fixed. But again, this is not a this is just one way. Okay, so well, I am not, but if I were strong enough, I could probably use some fancy orthogonal polynomials, as I show you in my motivation part, and just give you the answer for any lambda, any f, and for all values. I think, and I don't think that's impossible. It's just that it requires a lot more work. But that, I think that's an advantage of the field theory side. Good. So again, the story of what are the holographic objects dual to Wilson loop is, again, sort of, I think it was the first paper that one wrote after ADS-CFT paper. So essentially, the simplest thing is, if you want to compute the expectation value of a Wilson loop, you have to compute the area of the fundamental string. But Soo-Young Rhee also, more or less at the same time, understood that other branes will play an important role. And now in the context of n=4, Drucker and Fiola and also Yamaguchi realized that if you look at a classical D3 brane and a classical D5 brane, they correspond to Wilson loops in n=4 in the maximally symmetric or k-symmetric and k-antisymmetric representation. And then there was a stringy derivation of that by Gomes and Passerini, looking directly at the coupling in a string theory, etc. Now, for the context that we have here, which is type 2A, basically ADS4 times CP3, this gentleman here suggested that basically what we do is we take this picture and dualize appropriately, and then we conclude that the fundamental string in that supergravity background, ADS4 CP3, is dual to the fundamental representation, the D2 to the symmetric, and the D6 to the antisymmetric. So what I'm going to do now is to basically, again, my new results are in D2 and D6, so I'm going to explain, or I'm going to obtain the expectation value of the Wilson loop by looking at the action of these two objects. So here's for a classical DP brane. As I said, this is a description of the Wilson loop. So here's the action. I guess most of you should be familiar with this, even the students. Essentially, what you have, the branes that I'm interested here, that they are important in this context, they have electric field in their work volume. So this quantity would be non-trivial, and then of course these are the pullback of the 10-dimensional method. So if you have Ramon-Ramon fields, then you have to find the right form here, and it does contribute to the action. Okay. So the background is ADS4 times CP3. I'm going to use it in a particular parametrization, so I absorbing some constant to make it simpler. There's of course F2 and F4. This is the background with the Ramon-Ramon fluxes. Now ADS4 is convenient for this problem to look at the foliation in which I have ADS2 here, and then this coordinate U and then AU1. For CP3, I'm going to use this parametrization, which, as you will see, this is a parametrization of CP3. Let me leave it like that. Then maybe some people in the audience recognize that if I just look at this top, not this top line, if I'm sitting at a fixed alpha, which I will do for my solutions, then essentially the space-time that I end up with is very similar to T11. So it's called T11 tilde. But essentially you see that there are 2s2 and then this fiber S1. So we need to find the classical solutions. The classical solutions, so what I said is I want configure, in this case, I'm looking for an object that is 1/6 BPS to compare with the right string. The classical solution sits at U equals 0, and then therefore in my foliation expands ADS2. And then it also, so for the D6, it also sits at a constant point in alpha. Okay, so that's the classical solution. And so if I want to evaluate if I want to compute the action, I need to make sure that I do this Legendre transform to compute for a fixed P. P is the coordinate or the quantity that is dual to the electric field. So that's the number, if you wish, the number of fundamental string. The language that is used is the number of fundamental string dissolved in the work volume of the D-brane. So the equation of motion that I get from this is my action. The equation of motion essentially fixes alpha, the angle in this CP3, as a function of the flux that I put. So that's my classical solution again. Geometrically, it sits at U equals 0, and then at some alpha that is fixed by the flux that I put in the work volume. Yes?
So a question, so have you regularized this, or why is this
Good. So yeah, I have regularized it. Yeah.
So how do we know that the answer doesn't depend upon the regularization scheme or comparing the field theory scheme to the gravity scheme?
Good. So that's a good question. I will address it in a lot more detail. So I'm using, at this point, I'm just using the standard. I'm using the standard machinery that people use. So in fact, doing this Legendre transformation is the way to do this. Instead of doing subtraction, you're doing now something slightly better for regularization. But it's true that I will address your question much better later on. Yeah. Okay, so then I just okay, so this connects the number of fundamental string with the flux. Then the expectation value is given precisely by this expression. If you okay, it's written slightly different, but it matches precisely the field theory answer. So in fact, the way that I have presented here is backward, right? So Drucker, Plewka, and Young did this in 2008, and then in September I obtained the field theory part that precisely the leading piece matches. Okay, but so then there's some sanity checks that you can do. So it preserves, or it has the symmetry P goes to n minus P, which you expect for antisymmetric representation. So it's certainly the right object. Okay, so that's the part. So now let me discuss the classical solution for the D2. It's very similar. So again, it also has electric flux along. I'm using exactly the same foliation of ADS4. I'm using the same metric, same background. But now, so it expands ADS2 inside ADS4, sitting again at U = 0, and then it expands a circle inside CP3 with electric flux along its work volume. Here's the action, written, of course, already in the language of where P is going to be one of the charges that I want to compute. And then I just evaluate. For the classical solution is similar. And here's what I get. So what I get is exactly the same as in field theory, except that in this classical solution, my P wants to be K/2. And so that's a little bit peculiar, but this is a manifestation of the topological nation of Chern-Simons that I was explaining. So, okay, so let me make some comments just to clarify that life in ABGM is a lot more subtle than in the n = 4 case. So if you look at the kappa symmetry of this D2 brane, it really preserves a third of the supersymmetry, not a 6. So if you wanted to preserve a 6, the suggestion was to smear it along CP1. So that's already okay. That could be a complicated process if you want to then compute quantum corrections to this object. But this slide is essentially to show that the picture, even at the classical level, is fairly incomplete. But so the symmetric representation in n = 4, it really corresponds to a D3 brane, and this is that wraps ADS2 × S2 inside ADS5. Now, because the flux is along ADS2, in this case, the radius of this S2 can be arbitrarily large, which means I can have a representation I can have a symmetric representation with an arbitrary number of boxes, if you wish. That's what it means. So it makes sense that you look for some solution of D2 that is completely inside ADS4. And I have looked at this, but unfortunately, this does not have yet the properties that we expect. So what I'm saying here is going a little bit into a tangent, and it's mostly for experts. But what I want to emphasize is that throughout ADS-CFT, we have had this idea of the giant gravitons and giant branes, and they usually come in a particular form. And what we see is that in ABGM, that's not the case. Okay? That is a slight departure from this for this law that the symmetric wants to live, the object that is in the symmetric representation wants to live completely in ADS, and the object that is in the antisymmetric goes to the S5 or CP3. And the reason why we want the antisymmetric object to go to wrap S5 is because in S5 you have a maximum radius, which means in the symmetric representation you know that you have a maximum amount of boxes that you can put. So that intuition here for the antisymmetric, it works very nicely, but for the symmetric it's not quite working. Okay, so I will skip this because this is a little subtle about the half BPS. But what we know for a fact is the following. So I will talk a little bit more about representations of these objects. But if you look at the half BPS object, which in n = 4 was a point on S5. So here you might expect that the natural object is a point on CP3. So CP3 has the isometries of CP3 is U4, which of course correspond to the asymmetry of ABJM. But if you pick a point in CP3, it will give you a CP2, which will have a U3 as isometry. So that's that's telling you also, and you will see this in more detail when I discuss the flotation, that there are objects, classical objects, that are missing. In particular, all these half BPS objects, they must correspond to either a D2 brane that wraps a circle inside CP3 so that it has CP2 transfer, or a D6 that completely wraps CP2. These objects are not in this description, but they are useful. Okay, so I know again some of these remarks are very technical for people who actually think about this often, but the main take home is that even at the classical level, there seem to be a few configurations in ABJM that should correspond to Wilson loops that has not been constructed at the list. Okay, so now as I said, my talk is one loop holography. So I want to do one loop holography. So I will show you what is standard and what is done standardly in this case. So what I have already these classical configurations, and what I need to do is to look at fluctuations around this classical configuration and then integrate over the fluctuations. So for the D6, sorry, so it's a 7-dimensional world volume. So I have 3 scalars that correspond to normal directions inside ADS4 and CP3. So I have 2 directions that describe embedding ADS2 inside ADS4, and 1 direction that describes this T11 tilde inside CP3. So there's again, this is now very standard in the literature. There's a geometric way to look at these fluctuations using the geodesic map. And of course, I have to look also at the fluctuations of the gauge field. And again, even though it's technical, the conceptual is very clear. I have a surface that is classically given by some embedding, and I am now looking at all possible fluctuation of that embedding. And again, for the D6, I will have 3 normal directions, so these are the 3 scalars, and then there's a gauge field. So so I will not bore you with the details, but this is the answer. So these are fluctuations that live in this 7-dimensional space. So this is ADS2, and this is T tilde 11. And what I have is the scalars that I just described. Now they have basically a massive term. There's a coupling between the 4th scalar in CP3 and the gauge field. Okay. And then there are terms that are, these terms are fairly, well, okay, they were not there in the n = 4 case, and they have to do with the fact that the C3 form is non-trivial. So this is the bosonic part. Again, it's certainly, well, let me show you this is the fermionic part. It's again some 7-dimensional theory. I can compute it very explicitly. Here this is the one that acts on T tilde 11. So the key thing that I want to explain is that there is a prescription. So all I have done here is use a prescription from I show you the action of DP branes, the bosonic part, but there is a full D brane action. In that full D brane action, I have the bosonic part and the fermionic part. It's completely supersymmetric. It has all these non-trivial mixings, but this is the Lagrangian, or the action that governs the fluctuation. So now what I need to do to look at the one loop effective action is, of course, integrate the fluctuations. Okay. But before I do that, let me talk about the D2 brane. For the D2 brane, again, everything is very similar. There are more normal directions. There are more normal directions. 2 and 3 are, the embedding of ADS2 inside ADS4. But I have, again, 4 and 5 and 6, 7. They are all inside CP3. I, again, have this very interesting mixing terms. Also gauge field. And here's my Lagrangian for the fermions. So I will not torture you with details, but again, these are just eigenvalues that characterize a particular decomposition of the gamma matrices. So that's so let me make some comments about the structure of the fluctuation. So again, in the case of D6, just to summarize, I have two scalars that describe the fluctuations of ADS2 inside ADS4, and I have one, and they have a non-trivial mixing due to the fact that C3 contributes. For the D2, I have, in addition to these two scalars, I have these other 4 scalars, and they have so their covariant derivative has some contribution from the fact that the Norman bundle is non-trivial, and then there's the mixing between chi4 and the gauge field. So once I have all these fluctuations, what I need to do is to look at the spectrum. So I compactify on S1. This is, again, this for the D2, the work volume was ADS2 plus S1. So I now look at these numbers, and they are the conformal dimension of the operators due to these fluctuations. I have also for the fermions, this is the spectrum. You can I will know this is again the key thing here is what comes is that I can organize. This is like an important check that all my fluctuations always have to get organized in terms of supermultiplets corresponding to the symmetry, to the preserved supersymmetry group, which I will show you right now. So let's discuss. So here's the answer. For the D2 excitations, they have to be organized on this OSP4/2. So again, let me remind you, this is the Wilson loop, and it preserves 1/6 of these 24 supercharges when this matrix is taken to be like this. So at this, even at this level, just without going to the holographic side, but on the field theory side, you see that so on the field theory side, let me remind you that the supergroup of APJM is OSP6, right? /4, and basically the SP4 is isomorphic to SO3,2, which is the conformal group in 3 dimensions. Of this conformal group, there's a subgroup that remains, that is preserved by the string, and that's contains an SL2R part, and this comes from P0, which is translation along the line, then dilatation and special conformal transformation. There's, of course, another U1, but the key thing is that I have SL2R. Now, the SU4 asymmetry gets broken down to SU2 cross SU2, and you can see that this matrix is precisely the object that does the breaking, and it preserves this changing of C1 and C2 and C3 and C4. So the bosonic subgroup that is preserved by this configuration, and I have just argued from the field theory point of view, but I can as well or similarly argue from the holographic point of view. This is the bosonic subgroup that gets embedded into this supergroup. So now what I need to show to be, again, as a sanity check, is that all the spectrum of the fluctuation that I derive has to be organized in representations of this supergroup. And indeed it does. So again, in this case, so I can look at my supercharges and think of them as 4 of them are creation, 4 of them are annihilation. So I have 8 supercharges. So this is 1/3. This is for the D2 brane, and essentially this is what has to happen with the ADS2 quantum number. And this is the degeneracies, and this matches precisely the table that I show you. Now, and this is again one of the intricacies that I was mentioning about supersymmetry and ABGM. For the D6 brane, that preserves 1/6. So I only have 4 supercharges. So my table essentially goes, has to be half, and it's completely different. But I have checked that it indeed it fits into some supersymmetric structure. So I think this is the data that I need to compute the one loop effective action, which I should compare with the subleading terms. I have not done that yet. There are many reasons why this is a subtle, but it's a matter of just agreeing, and I will show you some of the simpler problems in ABGM that are not completely clear. So that's why I'm a little hesitant to have a explicit expression, but I have shown to you that I have all the ingredients to do that. So that's the part of one loop holography. Now, what I want to now take this opportunity to make some comments. So one of the comments is that this might look like a complicated argument, but normally when you think of localization, the simplest example of the canonical example is on a sphere, and it be S4. So for example, Pestun showed that the expectation value of the Wilson loop becomes a Gaussian matrix model on S4, and the work of Kapustin is on S3. But it is more or less, at least from the supersymmetry point of view, one can ask, can I also localize in non-compact spaces? And in fact, there have been some recent work by Narayan and collaborators, and also Martelli and Murthy, trying to localize just a field theory on ADS2 or in ADS3 in this case. So one spin-off of these D-brane actions that I have presented here, they are in fact supersymmetric field theory. So if you look at the structure of the multiplet, there were some chiral multiplets and some vector multiplets, and it is of course supersymmetric, and it is of course defined on ADS2 cross S2 and ADS2 times T11. So in this sense, holography naturally. So you don't need to go in the route of I know how to do localization in compact spaces. Can I also do it in non-compact spaces? So if you follow holography logically, it gives you explicitly constructions in which you have supersymmetric field theories that live in non-compact spaces. So that's, I think for me, it's interesting that this conceptually appears here. Now, okay, so this is a comment about order of limit. So one important thing that I think is very useful is, again, knowing how when you look at the D-brane action, you can think of the leading. You can think of the main coefficient as essentially an H bar. So the parameter in which you're really expanding, in which you're really computing. And if you follow this in the context of n = 4, it was understood that of course the fundamental string is an expansion in 1 over the square root of lambda. But following this, you can see that the D5 is essentially 1 over n the square root of lambda, and for the D3 you get 1 over n, which is related to the tension. Now in the context of ABGM, we see something similar for the fundamental string, but then the D2 and the 6, they essentially have the same coefficient. So there are some differences there as well. I also want to mention that there have been recent work. This is in July and this is in December by Chen Ling. I think she's a student of Sarembo, and then a Japanese group that essentially look at the matrix model computation in the context of n = 4 and try to say, I do not want to look at a 1 over n expansion, I want to just look at the square root of lambda expansion. And that was actually, it's a very interesting story because it essentially connects with expanding the Fermi-Dirac distribution for very low temperature. And this is something that everybody does in StatMech. Even on the graduate StatMech, you learn that there are corrections, the Sommerfeld corrections to the. So there's an interesting structure in the way that you compute the expectation value, and of course stack mech and other things. But more importantly, is this area here where you need to, even though holography chooses for you a particular way of expanding, you definitely need to understand how to compute in different directions. Like in this case, not 1/n, but a square root of lambda corrections. So that is the part that I mentioned at the beginning that was related to the new work that I wanted to report. So again, I summarize. I had done a matrix model computation for M-symmetric and anti-symmetric Wilson loops. I have also done the holographic computation, and they match a leading term, a sub-leading term. There are subtleties that I have not, I'm not ready to put all together. So I also want to, I will continue now saying that, explaining that there are other problems or other opportunities, if you wish, in the context of ABGM. So one particular thing is this computation of, from the field theory point of view. Again, this is a computation that I would have liked to be able to do for the K-symmetric and K-antisymmetric, but from the fundamental, there's an exact expression in terms of area function. The denominator is just the partition function of ABGM, so don't take the denominator too seriously, but the numerator is the expectation value of a half BPS Wilson loop, and this is exact. So a very natural thing is this would be the analog of the Dross, or the Drucker-Gross-Seiling calculation. Again, supersymmetry and localization give you an exact answer, and then you can ask, what is the object that the natural object is, of course, a string. So here is the regularization that I'm using, right? So I'm just, so this is my evaluation, and I essentially use subtraction. For the fundamental string, I can use subtraction, which is simpler. And you can see that, of course, the classical piece matches very nicely the field theory. But if you look just at the one-loop determinants, and you compute, this is, again, just using Hill kernel. These are well understood objects in ADS2. What you get is that the effective function for this half BPS Wilson loop is 0, which is not the field theory result. So again, there are things to clarify. So going back to Igor, so you see the log of lambda here does not come with a 3/4. So here there must be the case that if you want to stick to the interpretation in terms of 0 modes, then there must be 4, because the 3/4 became a 4/4. And that is kind of confusing, at least because if I'm thinking of this coming from string theory cares about the topology of the worksheet. It doesn't necessarily, well, okay, as far as we understand the way that we fix these Go 0 modes, doesn't dramatically change when I do it in type 2A or type 2B.
Suppose you expand in the M theory limit, like if you keep K fixed and large, then
In the M theory, so in the M theory limit, I will have to look at the membrane, or so it's slightly different. But I'm just saying that this is what so this very, well, okay, I cannot get it from holography, but even here the expansion tells me that if I want to justify holographically having minus log of lambda, I need 4 0 modes, which would be different from what I needed in type 2B. Yes?
So in case of manifold 4, there is also a discrepancy of this sort, right?
Yes.
The exact result has log lambda, but the calculation in the with the string does not give you log lambda.
Does not? No.
But what about terms which are suppressed, like square root of lambda, like higher terms in this expansion? Do they match, or nobody calculates?
No. The leading term, the leading term matches. The first sub-leading term doesn't match, so
yeah,
people
but
stop.
The next one.
No, people stop at this. As far as I know, maybe Martin knows. I think that people are.
I'm asking about the one loop, because this is the presumably 0 mode, but then there is also one loop calculation, right? Which would be 1 over square root of lambda suppressed or something like that.
No, but that's the con. Log of 8 pi, or what you take con. So the square root
Yeah,
of
yeah,
lambda
so I-
divided by 4.
So if I take, so I mean, one way of doing is take square root of lambda out, and then you will see that this is what we're comparing.
Ah, this is the
Yeah,
one.
yes.
And if we look, it will be 1 over square root.
Total no beta calculation.
No. Okay, so good. So again, there's all the wiggle room here that people, and this is where I have my long diatribe about classical solutions. That maybe this is not the right classical solution. Maybe you need to smear, and this might as well be true, but this needs to be spelled out more carefully. So this is another thing, and this is again more similar to what I discussed in Purdue. In fact, there are these strings. These are the cap string also in ADS4 times CP3, and you can again. This is work in progress with many people that are reading here. So Alberto Faraggi, Vimal, my student, Guillermo Silva, who's visiting IS right now, Diego Trancanelli, and Eduardo Vescovi. So you can also again go back, find the classical solution, look at this is part of the fluctuations. I have spared you many details, but again there, the field theory answer is precisely this, and it comes from these four modes. So this is the idea that I mentioned at the beginning, that playing around with this kind of calculation is also giving us hints that even in the bulk, because we know that the full answer, so there are of course divergent pieces that come from other terms, but they cancel between fermions and bosons. And the whole contribution comes from these four modes, for a particular expansion of these four modes. So this is again empirical evidence that even on the holographic side, there seems to be some sort of localization. This is something that again is not, it's more like it's hard to argue with a straight face, because to have localization you need an off-shell supercharge, you need a lot of ingredients. But on the face, I see that the full answer is recovered by just looking at some of the modes, and all of the other, what they do is noise. They cancel against each other, and the one loop effective function from this kind of a string comes again from only three modes. Again, because I have done this computation also in n=4, I know that in n=4 I have 3/2, which also works very nicely with the idea of the modes that we were discussing. Okay, so again, I'm more or less concluding this part. So ABGM provides another empiric example of bulk localization. This is a little bit like a blue unicorn, because again, if you just say write down the facts, you have no right to hope for that. But once you do all the steps and do the computation, you see that the answer comes from 4 specific modes, and that really smells like localization in the bulk. And it would be nice, of course, to pursue this idea. See, maybe we can have a localizing supercharge that is not completely off-shell, but can do the job. Can do the job for you. And of course, it would be nice to push this. So the idea, let me emphasize here, the idea of looking at this configuration is again that when I compare the quarter BPS to the half BPS, they have the same worksheet topology. Therefore, many of the issues that come from extreme perturbation theory should cancel when I look at the ratio. And indeed, I really get rid of all the log of lambda terms. They completely cancel, and what I get is something that is just a parameter in the solution. Okay. So I think that what we need, that one way to go about this problem is to find more situations like this where you can really define a comparison that is highly well defined, or as well defined as possible. So now I have a few more minutes, so I will. This is a lot more speculative. The other computations were just computation, but I think that this is very interesting, and I would have never thought about this had I not been doing this kind of exercise. So this is work in collaboration with Ioannis Papadimitriou, and essentially the question is very simple. So holographic renormalization is a very powerful technique. It's very well established. It has clarified many things, anomalies in ADS, CFT, etc. There are many reviews of the subject, but in every review, especially the latest review, it is clear that the main conceptual framework is the Hamilton-Jacobi equation. So in fact, your own shell action is a solution to the Hamilton-Jacobi equation. And that's it. So one problem that I have is to say, okay, is that the last word? So does that give me the effective action that I need, or do I need to revisit this story because I'm looking at holography beyond one loop, right? Or at one loop beyond the classical part, and the Hamilton-Jacobi gives me only the classical part. So one natural thing is to ask, and this I spent many afternoons with Ioannis at ICTP discussing this. So can we modify the holographic renormalization in a way that I get something that becomes Hamilton-Jacobi perhaps at 3 level, or this is the classical piece, but then I can get something more quantum. And the most natural idea was to consider the Wheeler-DeWitt equation as a quantum generalization of Hamilton-Jacobi, and therefore re-express holographic renormalization in a way that in this classical limit I just get the on-shell classical piece of the action, but then I can get the other corrections using this formalism. And
does this actually change the equations of motion for the D-brane and the bolt, or?
So let me show you what we have so far. It's not much, but I hope to report soon. So what I want to do is I want to now consider a Polyakov string. So I'm going to use holographic renormalization of the Polyakov string in asymptotically ADS space. So I write it like this. This is again more or less a standard in holographic renormalization. Here's the Polyakov action written in this parametrization, and this is my canonical momentum. And now what Wheeler-DeWitt tells me is to promote this momentum to an operator. This requires some sort of regularization, etc. And this is again very preliminary, but this is the action that you get as a solution to the Wheeler-DeWitt equation. The first part, if you look at this, well, I didn't write it explicitly, but this is a perimeter, the divergence that comes from the perimeter of the Wilson loop, and of course this we knew. But for example, this I hope that Martin. So in Martin's computation of the one loop effective function of the half BPS Wilson loop, there are divergences that are precisely. There are these kind of divergences, but there are other kinds of divergences. And now we have a framework in which I can recover the structure of divergences. So this, for me, is my way of answering, are you doing the subtraction, or are you regularizing this at the quantum level correctly? And this is sort of, again, this is very, very preliminary. And we want to do this for other brains, etc. But I think that just generalizing this idea that the renormalized action comes from Hamilton-Jacobi, if you move it into the Wheeler-DeWitt equation, you should get the whole structure of divergences, and then that can give you a scheme, a concrete scheme for computing and comparing with localization. Yeah. I will stop here. Thanks. Yes.
Not so much a question, but yeah, we've had issues recently with holographic renormalization too, trying to compare brain thermodynamics to expectations from field theory, and we really started to suspect this as being problematic as well, like maybe some finite corrections. So I like this.
No, this story is actually, there's also some work recently by Martelli where he actually adds some counterterm that exists only in the supersymmetric case. So in fact, the question is very obvious. When you do localization, you don't see any field theory divergences. You have a matrix, and that's it. So what must be happening is that on the gravity side is that you have to find in the presence of supersymmetry a set of counterterm that essentially renders your action equivalent without having to do what I have been doing here, which is essentially subtracting divergences because I know what they are. So there should be a more systematic way in which whatever the regularization that we use in localization is the same that we use in the holographic side. Yes.
Just let me clarify. So you think that maybe there is a normalized action, and if we calculate one loop using this action, then we will match the field.
Yes.
So I just have a naive question. Maybe that problem was resolved. I really, I don't know what was long ago, but I heard from Zaremba the following. If you consider the completely supersymmetric loop, such that the expectation value is 1,
Yes.
then there is still a problem because naively the determinants, one loop determinants cancel each other because of supersymmetry.
Yes.
But you have the number of zero modes which do not cancel each other. So naively you have the contribution from the zero modes on this string side, but you don't have it in field theory. So is it maybe possible to use this formalism to fix that problem?
I don't know. I mean, because you see, this is another very important conceptual thing. So what I do here, is I have my classical configuration and I use Nambugodu or something to get the.
I'm just saying that instead of considering half BPS, Wilson or quarter BPS, you can consider. I don't remember the counting, but I think you're considering quarter BPS, and I'm just saying you can.
No. The half BPS can be a straight line, in which case the expectation value is 1, or it can be a circle in which you have a non-trivial Laguerre polynomial. So when it's 1 and this.
You can have a round circle loop such that a round Wilson loop such that the expectation value is 1, right? You just need the phi is to run in the circle, right? You can have 2 round circle loops. One where phi's do not run on a circle, then you have a matrix model like this.
Okay.
I think it has less supersymmetry, but you can also have running on a circle, and then it's exactly like the line. It has expectation value 1, and this is like the exact result. But on the gravity side, you see this 1 at leading order, and then also see it at 1 loop because the terminals cancel. You have 0 modes which seem to contribute out of place. I don't know, maybe it was resolved.
No, that one I don't know.
I think it will be just maybe an easier, more supersymmetric relative of the problem you are asking.
I'd be happy to talk about it.
Yeah, I think we don't have log of L, no? Maybe in the
You do have log of L. You have epsilon. Actually, I spent a lot of time understanding because, again, so you have epsilon and then you have log of epsilon over epsilon. And that is kind of what I expect is going, because, okay, when I said L, my L has to be really perimeter divided by epsilon. So that's what I.
No, but when we do the calculation, see, we don't get log L. Maybe in the supersymmetric case it cancels.
No. No. I think. Okay. So what I wrote. So think of my L as 1 over epsilon.
Yeah. So you get that, and then you get.
When you do, actually, I know exactly in your computation. When you do, there is a part in your computation that you want to in Gelfand-Jarlom story where you want to. You have this fermionic operator and you want to change the mode number. When you do that change, there's a log of epsilon that you have to throw out, going from m integer to m half integer, and this is precisely this kind of actually my main question was this, because whenever we have this problem of regularizing a holographic configuration, we do it very ad hoc. So I regularize the classical piece and I show you, it matches, right? Already regularized. Then I go to the 1 loop and I get all the divergences, and then I also deal with those divergences by themselves. And that's not the way that it should be. It should be that I have one object, one general counter term that deals with all divergences at once. The classical piece, the 1 loop piece, all should be there. So that was really my main motivation to start to sit down and try to understand how to change holographic renormalization in a way that it also becomes a quantum object, in a way that it can really give me on the holographic side everything that I can compute.
I think that the cast gives log epsilon, but if it's smooth, you get log epsilon.
That I don't know. I mean, I think that this analysis requires that I have to stay away from I have to consider only smooth, because in fact, you see, this I'm trying to do in a way that is all diffeomorphic invariant, etc. So if I have discontinuity, it becomes a separate case.
I think there was a two-loop calculation for some.
Yes.
I remember the paper called two loops to two loops.
Yes, there's a two-loop. It's Roy-Ban, Arkady.
There was
but that was for rotating.
Two loops to two loops.
That was for
paper by-
rotating a string, I
by
think.
Staudacher, I think they looked at the surface with two circular loops.
Well, let's thank Leo again.